Hi, everyone. Welcome to the third presentation in this year's Databricks Tech and Career Talk series. I'm really glad that you can all join us. I'm Drew Pollan. I'm the Principal Academic Director of MIDS here at the iSchool. And tonight I'm pleased to introduce Dr. Srijith Rajamohan, who will lead the presentation and discussion tonight, focused on putting machine learning into production and sharing with us some best practices on managing scalable machine learning pipelines and lifecycle. Srijith is a senior developer advocate at Databricks, where he works on data science and machine learning problems. He's interested in all things related to the ML lifecycle and has a focus on natural language processing and Bayesian modeling. He recently launched a series of 3 courses on Coursera to teach computational statistics and Bayesian inference using PyMC3. He was a computational scientist from 2014 to 2020 at Virginia Tech, where he worked on natural language understanding using deep learning techniques, Bayesian inference, and reproducible and scalable infrastructure for machine learning problems. He's a graduate of the University of Tennessee Sim Center, the Center of Excellence in Applied Computational Science and Engineering, where he did his thesis work on computational electromagnetics using the finite element method and earned a doctorate in computational engineering in 2014. He also holds a master's in electrical engineering from Pennsylvania State, where he worked on implementing neural networks for computer vision on the IBM cell processor. So welcome, Srijith. Thanks so much for joining today. Before we get started, though, I just want the audience to know that we're going to accept questions throughout. So please just post them in the chat or in the Q&A panel, and we'll find an opportune time to address them. Srijith, shall we get started?
Sounds good to me.
Thank you.
Well, thanks, Drew, for the introduction, and thank you, everyone, for attending this session today. So today we want to talk about machine learning at scale, and specifically, how do we put our machine learning projects into production at a large corporation or if you're a large group. So a lot of the things that we're going to be talking about is at a high level or conceptual. So it's not going to be a technical talk where we're going to talk about Delta Lake or Spark. A lot of these things will be introduced or mentioned as tools to be or frameworks to be used in the context of various portions of the pipeline. But generally, the goal of this talk is not to introduce a specific framework. So when you're getting started on any scalable machine learning project or deep learning project, there are several things you need to consider and ask yourself before you get started on this journey. So, for example, what is the reason that you're creating this model? What goal are you trying, or what problem are you trying to solve? What's the goal of doing this? What training data do we need to use? And is it proprietary data or sensitive data? What type of storage are we going to use to keep the data? What is our data retention period? Then you have to consider the type of the modality in which the data is coming in. Is it real time, or are we doing batch processing? How are the models being used, and who's using it? The type of persona. Is it used by a business analyst? Is it going to be used by a non-technical stakeholder? The kind of environment this model is going to be used. Is it going to be an exploratory analysis environment, or would it be a production environment? Because these two have different requirements for SLAs and such. Is the model performance being measured regularly, and is the model being updated? So there are many situations when we've trained a model, but after a period of time, things have changed either because the data distribution has changed, or the way in which the problem is defined and solved has changed as well. So is the model well documented to ensure reuse not only by yourself, but other members of the team? Is the model deployment process being automated? So as you scale up your problem, not only do you have to monitor and automate your model training process, but the deployment has to be pretty seamless as well. And last but not least, is the project that you're undertaking have institutional adoption and support? It's rarely the case that you're able to be successful in something like an ML project without adoption at the highest level. So it has to align with the business goals. So to start off, just want to give a little bit of overview of what the ML team looks like for most industrial settings. So you'll have a subject matter expert or an SME who has a deep understanding of your business problem. These folks usually need to be integrated into your ML lifecycle. And then next, you have the data scientist, who I would like to call the quarterback of your team. So obviously, this person needs to have mathematical modeling skills. But more importantly, this person needs to have communication skills. So they're the person who's going to be interfacing with various different personas, getting requirements and translating needs from the SMEs and moving that pipeline along efficiently. Most teams would also have a data engineer whose primary responsibility is managing the efficient flow of data and data pipelines. And depending on the size and the scope of the project, you may also have an ML engineer whose responsibilities may be split between a couple of different titles, like an ML architect or a DevOps engineer. So for example, ML architect's responsibility would be to design, manage, and scale the ML infrastructure. A DevOps engineer, on the other hand, is primarily responsible for deploying and operationalizing the models. So the goal is to ensure that these models are always up and available for use. So obviously, you also want to take into account what best practices you want to enforce in these projects, starting with software engineering practices, code quality practices that your software engineering colleagues use also apply to most ML projects. Apart from that, you also want to validate your data, make sure that you ensure proper data types and formats are fed to your model. You want to make sure that there's no data drift, for example, which can render a supervised model pretty ineffective. Another thing you may want to consider is versioning and tracking your experiments like code. For example, if you're changing hyperparameters, your input data, for example, or your code, you want to make sure that you're logging these systematically, you're making these changes systematically. So not only do you understand what changes were made, but other teams can also follow that train of thought. You want to monitor predictive performance over time. So ensure that the model performance does not degrade over time. You also want to ensure that model fairness across different classes of data are being maintained, or you want to mitigate any sort of bias. So what does this ML ops pipeline look like? So ML ops just stands for, it comprises your machine learning model plus data ops, everything that you're doing with your data. Think about GitHub for your data, how you're going to manage your data over that entire lifecycle, plus the DevOps. So all these three components make up essentially what's called machine learning operations or ML ops. So that pipeline now looks something like this. So you build your model, then you're testing that model, putting it into production or deploying it. Once you have it in production, you want to monitor the performance. And whatever feedback you're getting, you want to actually put that back into your model and continue that cycle of building, testing, and iterating. So that's roughly what our model management lifecycle looks like. So we'll walk through each one of these phases of our lifecycle and see what needs to go into those phases. So we'll start off with the model build. So what should happen at this stage? We're ensuring that we're building and verifying the model with our data. So you're ensuring that you're solving the right problem here. It's very critical. And you're estimating the required performance metric and choosing the model with the lowest complexity. And this is also a good time to mention that you want to start addressing things like fairness and reproducibility at this stage of model design, because the longer you wait to address these, the harder it becomes to actually re-engineer these problems. So you may want to start thinking about these things as soon as you start devising the algorithms. You want to ensure that functional and unit tests pass for all modules. So, define these tests carefully. All artifacts are version controlled and saved. So by artifact, what I mean is all the code and the associated model, configuration, data files, the environment, and documentation. So use tools such as MLflow for saving these artifacts. One of the first things you would need for training most ML models is data. So first of all, start by asking, is that data already available? And what's the provenance of the data? Is it openly available, or is it proprietary data? Is it static data, or is it continuously updated data? If it's not static, is it processed as a batch or in a streaming fashion? And where's the data going to be stored, and how is the data going to be stored and versioned? Then there's a question of where the data is going to be stored. And if it's stored off-site or away from your training infrastructure, how do you move it to the training stage? So when you start doing these things at scale, these issues become quite challenging and need careful thought to address it. Then there's data quality. The data that you're ingesting, is it reliable, or do you have to denoise it in order to feed it to your model? And finally, does the data have to be labeled, because there's probably a cost associated with doing this. So once you have the data, you start asking what features in the data are important in the predictive process. It's rare that you actually can just start using that raw data, because most of the times the models are working on processed or extracted or derived features from this raw data. And for this, consider using a feature store. It enables feature discoverability and reuse. It also allows you to track the lineage of data for that predictive modeling process. So you also want to start thinking about compliance at this stage. You want to remove any protected features and identifiable information from the data. Start accounting for bias and make sure that you comply with all data regulations, privacy regulations like GDPR or CCPA. And also start thinking about how you're going to provide access control for this data. So once you start training, the infrastructure is something that you have to account for. Are you going to use CPU or GPU for online or batch training? So in online training, you're incrementally updated with new data, and this is useful in a streaming data scenario. Now, keep in mind, this is not a stateless process. It's often the case that your model can get outdated and it needs to be retrained with new data for accurate prediction. So think about how often you need to actually retrain this model. So the frequency of retraining needs to be balanced with the cost of retraining, because it's usually not a cheap process. Whenever you're training your model, you also have to think about doing this in a systematic fashion. So tools like MLflow are designed to help manage this process for you. It helps to track your variables, your hyperparameters, your artifacts. You can also version control models using the MLflow model registry. The goal of these tools is to ensure reproducibility of your ML training or your ML modeling. You can perform hyperparameter tuning, which is done to identify the best performing model. So it's not necessarily the model with the best metric. You also want to think about how it generalizes. So generalizability and model inference times are usually more important than the model with the best metric. Once you've done that, you can also use an AutoML tool or framework to identify the best class of modeling techniques along with the hyperparameters. So a few thoughts about how to perform training at scale. So usually it's the case that we're doing distributed training and not just on a single node. We can perform either data parallelism, or we can use either data parallelism or model parallelism for distributed training. So in data parallelism, the data is divided among the different nodes. And in this case, the entire model is copied to all the nodes. The gradients are now communicated back to all other nodes to update the model. And this can be done in a synchronous or in an asynchronous fashion. The only problem with this is that if the model size is a concern, because the same model is now copied to all the nodes. So this is where model parallelism comes into place. So in this case, the model is now divided among all the nodes. It only works, however, if you can take advantage of task parallelism in the model. So most machine learning models or architectures cannot take advantage of model parallelism. So this is something that's very specific to certain problems. In this case, however, model size is less of a concern compared to data parallelism.
Srijith, there's a question from Avinash, who's wondering, do we use EDA for feature discoverability?
So the way I define feature discoverability is at least from a feature store perspective, is if you are using, let's just say, EDA to discover, or ETL and EDA to extract features from your raw data. Now you have some derived features. So yes, you use EDA to create those features if you don't know what's in there, but if it's a pipeline, it's already extracted those features and you have it stored somewhere. Now, think about the case where you have other team members or other teams in your organization who need those, needs that exact set of features. And in that case, you don't need to actually go through that cycle of ETL and EDA to extract those features. If it's stored properly and it's documented along with the metadata, they can just simply grab and reuse it. So that's what I mean by feature discoverability. Does that make sense?
Makes sense to me. Yes.
Yeah.
Thank you.
So going back to training or distributed training for machine learning or deep learning. So in deep learning, there's something that we need to consider for synchronizing our distributed training. So a couple of ways in which this can be done. One is the model parameter server approach, and the other is the all-reduce approach. In the model parameter server approach, central servers hold all the shared parameters, and the workers receive updates from the central server. The problem with this approach is that it is harder to scale, and speed up now depends on the overhead of communication with that central server. The all-reduce approach was designed to minimize this issue. And in this case, all the machines now store the shared parameters. In this case, there's no central server. And some examples of architectures are the ring all-reduce and the tree all-reduce. So if you've used Horwath is using an all-reduce algorithm to perform distributed training. A few things that I just want to touch upon. We won't go into a lot of detail, but just wanted you to be aware in training is quantization-aware training, federated training, and privacy-preserving learning. So in quantization-aware training, what we're doing is we're using lower precision weights during our training to minimize the memory or compute requirements. So if you use GPUs for training or for inference, you probably noticed on more than one occasion that you run out of memory, or you get out of memory error. So that's a pretty common thing to happen on GPUs. So what quantization would do is that it minimizes the amount of memory required for you to store that model. So as a result, you also have the dual benefit that your model training or inference would also happen faster because it needs to only operate on a smaller set of data or smaller stored data. In federated learning, we're using decentralized learning with the federated averaging algorithm, for example, from Google. So in this case, we keep the data on the device, and it's not actually moved to a central server. The model is now updated with the data that resides on the device, and the updates are now sent back to that central server. The updates from all these devices are now averaged. In privacy-preserving learning, what we do is that we learn from data that's encrypted, or the user or the humans have minimal exposure to the data. So the next topic that I wanted to talk about is reproducible ML. So we want to start off by documenting the assumptions about our data and the problems that are being solved. It's obvious that our algorithms need to be reproducible. It's needed for obviously the fact that you need to get the same results every time you run it, but you also need it for governance or compliance reasons. Data versioning. So you may want to also think about using frameworks such as Delta Lake for data versioning. So along with your model being versioned, you also have the data that's being stored every time you're training or performing an experiment. Also consider using a feature store to track and save these extracted features, so it's easier and almost always faster to use them in an ML project. So we talked about the algorithm and the data, and usually an aspect that gets overlooked is the environment. So if you're a practitioner, I'm sure you've come across a scenario where you try to update your environment and suddenly your code doesn't work. So you want to also apart from logging your data and your code, log the environment as well. That includes your source code, your libraries, any infrastructure. And lastly, you want to design and log the output metrics for reproducibility. So think about what's the best way to ensure that I am making sure that the results that I'm getting right now are exactly what I got before. So think about the metrics that would allow you to ensure that these experiments are exactly the same. So explainable AI has gotten a lot of press lately, and rightfully so. One of the big concerns that folks have with using something like a neural network is it's used sort of as a black box. So explainable AI or XAI is designed to address that. Why do we have a certain output Y given an input X? So we no longer like the idea of the output being a black box. So we want to understand what's causing something to happen. there's a question. So the question is, once a model is deployed, how frequently does it need to be updated in general? So there is no one size fits all answer to that question. It really depends on the context. So I do have a slide where we actually talk about that, but the quick version of that answer is essentially, you want to understand if the data distribution changes. So most times the data drift is due to one, it's just a non-stationary process. So the distribution of the data changes. So how frequently that changes, one can never tell, right? It really needs to be monitored. That's why model monitoring is a very critical aspect these days. And there are specific tools that addresses that. So there are probably things that never need to be updated. And there are probably things that need to be upgraded fairly frequently. So it's a wide range of frequencies or timescales, I would say. You want to ensure that the results you're getting fall within a certain percentage points or standard deviations of what you expect to result. So it's sort of a, ML modeling is a little different from your software engineering project in the sense that it's kind of hard to understand or predict what's right. So it's a probabilistic problem that we're solving as opposed to a deterministic one. So you want to think about the solutions that I'm getting no longer look like the ones I should be getting. So it falls outside of a certain standard deviations of what I should be getting. At that point, you may want to start considering, retraining it. A lot of domain knowledge expertise goes into determining that. So, which is why I said that SME really needs to be throughout that life cycle of your ML project. You can't just talk to that person, get requirements, and then say never see them again. That's unfortunately not how ML works. It's a very collaborative process. When you have something like concept drift, for example, you need the SME to help define the idea of what that concept is. So the example that I'm using later is fraud, but you can't really know what fraud is unless you talk to the subject matter expert, for example, in a financial sector, to understand how to look for fraud. I'll explain that in a few slides, so bear with me, but does that answer that question? Sounds good. Yeah, going back to the idea or notion of explainable AI. So we want to understand how, why features cause a certain result, right? So there are various ways in which we can actually determine this. Some techniques that are currently used are Shapley values, Lime, permutation feature importance. So these have different, each one of these have different advantages and what they provide, but these are standard techniques that are available in toolkits like scikit-learn that allow you to understand why a certain result was produced. Also have to understand that in many domains like the financial industry, solutions obtained from, for example, deep learning with neural networks cannot be used. These results are not generally understood to be explainable, and ML algorithms are preferred as opposed to the deep learning counterparts. Also think about GDPR. So GDPR, you have to explain what logic is being used, what process is being used, and what the impact of these decisions are that are being made by the algorithm. So a few things to think about in terms of explainable AI. So that brings us to the next stage, that is model testing and preparation. So you performed your experiment, you built a model. Now you're at the stage where you need to hand this off. So usually what happens is you have a data scientist who performs the modeling, and you have to interface with the data engineer or the ML engineer. So the goal at this point is to make sure, as a data scientist, you're minimizing the amount of work that the data or ML engineer needs to do. So a few things that you can do is make sure that your model is ready to be productionized, or your model is convert the model to be production ready. So the ML engineer can help you get that model in the correct deployment format. You can also reduce the model footprint. So use things like model quantization, pruning, and distillation as appropriate. So the goal is to get the model that does what you want it to do with the minimum footprint in terms of size and computation time. So if you're using this in a mobile setting or an embedded device, account for power considerations. Also, if you're using this as a real-time model, account for latency considerations as well. Ideally, you may want to think about all these things during the model design stage as opposed to when you're ready to hand it up. As I mentioned earlier, the sooner you start thinking about these things and accounting for them in the design stage, the easier it is to solve these problems. So now you have the validation step. So make sure the production-ready model performance is sufficient on the test data. So a few things to consider. The test data should be representative of real-world distributions. It should also cover extreme events that are unlikely to occur. And even if you think you have these covered, you may also want to test it on a sample of the current production data just to be sure. You also want to ensure the computational performance is tested, as I mentioned, the compute time and the memory usage. Compute and memory usage, and also the solution time. You also want to establish well-defined checks for model performance with assertions. Also assess model fairness at this stage. So another thing to consider is portability of your model. So portability and reproducibility sort of go hand in hand. So this can be addressed either using file formats such as ONNX, or you can think of it in terms of how you structure that project. For example, MLflow projects are a set of conventions that allow you to save your code and your data and your environment such that it's easy for someone else to take it and reproduce it. So either you can deploy it to a different environment seamlessly, or you can share it with your colleagues or your team members, and they can get started running that fairly seamlessly. So these are two different ways of doing, making sure that your ML projects or ML code is reproducible. Also, if you're working within Python, consider using reproducible environment files. So conda and virtual and env makes it very easy to reproduce your environments. However, if your environment consists of more than Python code, consider using containers. So Docker and Singularity are two examples here. Docker containers, for example, can be easily deployed to Kubernetes clusters, which take care of load balancing, scaling, and load management fairly easily. And neither of these options work for you. And if you have to use something like virtual machines, consider using playbooks, Ansible playbooks, or Terraform and Puppet to make sure that you can deploy these or provision and deploy these virtual machines seamlessly. At this point, I'd like to talk about some critical issues in ML that probably fits in at this stage. Is the first thing that I wanted to chat about is governance. So governance comprises at least of the financial, legal, and ethical governance aspects. So there are industry-specific regulations that address the use of these models. They usually consist of process and data governance. What we're trying to do is we want to account for bias, lineage, data integrity, explainability, and reproducibility. Keep in mind, all data privacy regulations, such as GDPR and CCPA, that normally applies to data, also applies to ML. So make sure you're accounting for that. Now, talking specifically about data governance, what does that address? We want to think about what data is available at what point in the ML lifecycle. So it encourages data sharing and reuse, and it eliminates duplication of work. We also start asking, is the data usable? We want to address data consistency over time. And this data integrity, what we mean by that is, are we sure that the data is of good quality, which in turn will result in increased confidence in the decision-making as a result of the predictions from a model using that data. Then there's data access and security. Think about compliance. And finally, accountability. Who's responsible for the data quality? So two ways in which we can frame data governance is for defensive and offensive purposes. So defensive activities are designed to minimize risk, for example, in compliance. And offensive activities are revenue generated. For example, if you're doing something such as modeling for churn, we're talking about who gets access to the data so that the data can be used for positive purposes or revenue generating purposes. Bias is something that I think most people are familiar with by now. So bias is defined as discrimination based on usually a legally protected attribute of a class. For example, race or age are two features that you probably shouldn't be using in any ML model. This could be the result of bias in our data that is a result of improper sampling or improperly framed problem statement. So that is, we're not accounting for the bias when we have limited amount of data. So it's just improper data science techniques. Or as we just mentioned, we're using features that have protected class status. So I want to actually separate a bias from fairness. So what is fairness? So fairness doesn't just necessarily mean things that are covered or subject to legal regulation. A lot of the times, the public opinion can also define what's fair. So the one thing to keep in mind is that the notion of this fairness also evolves over time. One thing you may want to think about, either as a consumer or a producer of ML models, is the notion of intentional misuse of ML or machine learning models, or the misplaced use of ML. So two examples in recent history are the issues with Cambridge Analytica, which was an improper use of intentional misuse of ML modeling, and the recidivism case that was used for assessing recidivism in the judicial system, which was a misplaced use of machine learning modeling. So that brings us to responsible ML. So what I mean by responsible ML is it has to be transparent, accountable, and fair. So you should be able to explain, for example, how various features affect the prediction. So we all already looked at that in Explainable AI. It should also be representative and not adversely affect a particular class. So this is needed for regulatory purposes because it can be unlawful to use protected features. You also want to make sure that worst case scenarios are assessed. So you're also making sure that you understand the various risks when you're making these decisions as a result of these models. And last, but definitely not the least, understand the limitations of the models and interpret these results correctly. So as a result of all this, we have this notion of trustworthy AI and ML. So organizations worldwide resorted to providing guidance or drafted regulations for how many of these ML systems should work in production. So according to the EU, for example, any system or model using ML can be considered trustworthy if it has continuous human oversight, if it's a robust algorithm and the implementation is also robust. It complies with all the data privacy regulations like GDPR and CCPA. It accounts for fairness, mitigates bias, and is explainable. It works towards the betterment of the target audience. And there are measures in place for accountability, such as data lineage tracking, data integrity, and model reproducibility. So it addresses everything that we've just talked about so far. However, many of these governance measures that we're putting in place in these organizations, you have to think about whether it's proportional to the problem that we're trying to solve here. So it needs to be proportional to the level of risk of the desired problem and the outcomes, also the extent of the impacted audience. Obviously, if you have an extremely sensitive decision-making pipeline, it requires a thorough governance process. So every component of the modeling pipeline needs to be examined, and training algorithms, reproducibility, explainability, documentation, testing coverage, infrastructure fault tolerance, monitoring strategies, everything needs to be thoroughly examined and continuously. And one of the best ways to do this is to ensure that your organization has a data steward that ensures controls for every step of this process. So their primary responsibilities include they're making sure the data has proper metadata, you have access control rules for storage and the data models. So the next step is model deployment. So this is again a concept we're borrowing from software engineering of CI/CD pipeline. So usually software gets built and deployed in a continuous fashion. Similarly, we can do something for machine learning models as well, where your models are integrated and deployed at a variety of frequencies. So this pipeline complexity can depend on a variety of factors. So for example, are you working in a startup team or is it a large enterprise? How many team members do you have? What is the infrastructure budget that you have? Are there any regulatory needs for this pipeline? And the criticality of the decisions made by these models. And the frequency of deployment. So generally, you want to deploy frequently in smaller increments. However, the problem with that is that you're adding on to costs of actually training and deploying. So balance these two appropriately. There are generally two deployment strategies that are used. One is called the blue-green strategy, where the new model is deployed along with the old one. And when the new model is verified, you shut down the old one. And there's the canary deployment. In this case, a portion of the data is redirected to the new one. However, both models are live now. That brings us to infrastructure. So where is the model deployed? So you can use either a self-serve or a managed option. So to keep in mind, there are usually high engineering costs for self-serve options. So you may want to think about some managed options for serving. Things like Kubernetes. So this provides scalable enterprise-grade frameworks, which itself can be either self-serve or managed. You can always perform model serving using some of the ML frameworks, such as TensorFlow serving and PyTorch serve. And then there are lighter weight open source serving frameworks like MLflow and Bento-ML. If none of these work, you can always use some of the data science platforms, such as the managed MLflow on Databricks. So when it comes to model deployment and serving, assess the scale of the problem. So for example, is this a one-off short-lived problem and it's fairly lightweight? Then you can use frameworks like Flask or Dash. You don't need to have something that's mission critical, as something that's heavyweight, as we need to do for mission critical or robust problems. So in which case you have to make sure the deployment standards are met, and you want to make sure the deployment is tested in a production-like environment. You want to test the model accuracy, check for governance guidelines, and stress test the application as much as possible. So the next step is model monitoring. We want to ensure that the models are performing as intended. So as I mentioned earlier, it's a little more difficult compared to software engineering to ensure that these models are performing as intended, because these are probabilistic models. So you usually have to perform a little bit of, you have to put a little more thought into designing these tests to ensure that they are performing as you expect it to. There are various tools to help you do that, but usually it needs to be done along with the help of the subject matter expert. Model monitoring is critical to the long-term viability of the models, and you have to make sure you have the infrastructure and the policies in place to do this. So model monitoring consists of three parts or three components, essentially. The first one is the DevOps aspect, which is you're assessing the model performance in terms of the speed, memory, and the compute resource usage. So make sure that they're all within the bounds of what's acceptable. Then you have the data science metrics. For example, this is where model degradation is being addressed. So this can happen from model drift, where you have incorrect or unexplainable or biased results as a result of various changes in the phenomena that we're trying to model. So two ways this can happen. The assumptions about the data distribution are no longer valid, or the assumptions about the relationship between the input data and the output labels are no longer valid. So we're talking about data drift and concept drift here. Then the third aspect to consider is the business concern. For example, is the model actually delivering value? So while everything is working in terms of drift and the DevOps metrics are within bounds, but are we actually getting value out of putting this model in production? And more importantly, is the value that's being delivered by the model outweighing the cost of putting this in production? So just to elaborate on model drift. So as I mentioned, there are two types of model drift, roughly. That is, one is data drift and the other is concept drift. For example, if you have, in data drift, for example, there's a change in the distribution of the data. So if you are using derived features, you can also change the distribution of the features derived from that data. Looking at an example of anomaly distribution, anomaly detection, the distribution of credit card spending, for example, is the use case that we're going to look at to understand data drift. So if the distribution of your credit card spending might have changed over a period of time, and we're using something like a threshold for fraud detection, you can no longer use that same threshold that you set maybe 5 years ago. So because if you do, you're going to get a lot of false positives. Concept drift, on the other hand, is the change in the relationship between the input and output. So looking at that same example, if the data distribution has not changed or if our spending habits have not changed, However, fraud is committed at, for example, charge X less than T. T is a threshold, but in several transactions for a total of NX. So if you're doing N transactions to get a total fraudulent transaction of NX, you can no longer use that same method of identifying fraud. So the definition of fraud is now different, and the concept now has to be redefined. So this is a little harder to identify. And most times it's not quite this simple, and you will usually need the help of the domain knowledge expert to help define this concept. So how do you detect data drift? So the drift can be a result of non-stationary phenomena, or it could be a result of improper sampling of the data for training the model. And how do we identify this data drift? Or technically, how do we identify the distribution of the data, or the change in the distribution of the data? You can use a test like the KS test for testing if the samples are from the same distribution. For example, is the current data that you're seeing the same, has the same distribution as our training data set? And if you have categorical features, you can use a chi-square test. You're essentially testing if the frequency of your test features match that of the training data set. Concept drift, as I mentioned, is a little harder to define, and usually requires that domain knowledge expert in the loop to help redefine that. So I'm not going to go into a lot of detail here, just wanted to call that out. Model monitoring for updated models. So there are two ways in which this is done, and it's pretty similar to what we talked about in terms of deployment. It's just a scenario and situation. It's being used is different, but the definition is the same. For example, in shadow testing, the new model is deployed into production alongside that old model. And that new model also predicts the results for an input, but these results are not returned to the user. However, now the results of the old and the new models are now compared. In A/B testing, that input is now split between the new and the old model. So the new model gets a certain number of users, but the old model also has a certain portion of the users. The results of either model are now returned back to the user. So they both get results right back. So coming to the end of this talk, so I also wanted to address, how the, various organizations put ML ops into production, the level of sophistication that they have in their pipelines. The first one is the simplest pipeline is the manual pipeline, where you're performing manual EDA, training, and validation. You're committing your code to the repository, then you're integrating that code into an ecosystem manually, you deploy and you monitor. So none of this is usually automated, and you require a lot of engineering or overhead to make sure that this pipeline is working effectively. So this is usually the easiest way to do things when you're starting out, but becomes cumbersome as your team or your project scales. Then you have the continuous model delivery. What I would say is the majority of organizations perform a version of this. You have automatic model training and tuning. The data statistics are automatically gathered or generated. The features from the data are stored in some sort of feature store, so it's easy to discover and reuse. You also use something like a model registry to store the models. You also have modularized code and standardized data. The third step, or the most sophisticated way of doing it, is when you have a continuous integration and continuous delivery. So in addition to the automated model building, you also have automated pipeline build. So all the components are the pipeline components are automatically pulled and built and tested. You also have something like a pipeline package store that holds all these verified pipelines, so you can pick a certain version of that. So to wrap up, MLOps is a rapidly evolving field. We've only talked about a very small portion of the MLOps pipeline. Modeling, once again, I want to emphasize, this is a very small part of ML in practice. So the rule of thumb is that most training or modeling is only 15 to 20% of the entire MLOps lifecycle. Keep in mind, the needs of an enterprise are vastly different from that of a small research group or organization. Assess those needs carefully, so you're not just following practices blindly. With that, I'll wrap up this talk and take any questions you guys may have.
Excellent. Thanks so much, Srijith. Yeah, so we do want to spend our last few minutes addressing any questions that you have. So Feel free to type them out in the chat or the Q&A panel, or if you want, you can just raise your hand with that feature at the bottom of your screen, and I'll enable your mic so you can ask your question directly. Avinash wants to know a little bit more about p-value.
Can you be a little more specific?
Avinash, what would you like to hear more about p-values?
There's a lot to be said about p-value. I'm not sure we have enough time for that.
Related as it relates to data drift.
Yeah, I mean, it's just a way of saying, you know, there's a difference that we're seeing sufficient. I mean, the whole idea of p-value is to make sure that, it's the best way to put it, the changes that we're seeing are as a result of the phenomena that we expected to be seeing, and it's just not random. So that's the whole notion of the p-value, right? So we're not just seeing that metric that we're measuring by chance. So we need to set some sort of p-value to make sure that the change that we're seeing is not a random observation. So that's probably the rough summary of it. But I could probably send you a little literature to read about that. It's a little harder to explain in this setting. I mean, you can also do that in a Bayesian context too, because now instead of a p-value, you have something like a HDI. All that it's saying is that we have a certain level of confidence that the metric that we're measuring now is different, and the difference is relevant, and therefore we can say with confidence that data has changed. Because how do we for example, I could just say we're looking at the F1 score, and the F1 score change is it relevant or not? How do we know that? We need some sort of threshold to do that, and p-value is just one way to do that.
Great. There's a couple of questions in the Q&A panel. The first one is, what are the top practices from a machine learning design patterns perspective?
Could you repeat that again?
What are the top practices from a machine learning design patterns perspective?
It is a very open-ended question. Top practices. So many ways I can address that, but going back to, let's just look at this. So there's best practices for data. There's best practices for managing your code, best practices for your deployment, best practices for monitoring. The data is easier to talk about because Delta Lake, for example, is you're managing or versioning your data such that you know what data was used when, and you can go back to an earlier version of that data and use it, make sure that the results are the same. So obviously you want to ensure that you have good best practices for versioning, reusing your data, data access control, data discoverability. Design patterns in terms of modeling. I'm assuming this question is more to do with the architecture and modeling techniques. Is that right? Or is it to the entire life cycle?
It's from an anonymous attendee, so I'm not sure we're going to get a response to your question, Srijith.
Yeah, that's okay. I'll just address the
yes,
the modeling part as well. So okay. If you look at ML flow, for example, you have three components there, which is you have experimentation tracking. So when you're performing the modeling experimentation, you want to make sure that you track it. But I would say from a experiment design perspective, ML flow projects is more relevant because it is essentially an opinionated way to store your ML code. So it's saying that my ML code should have my environment specified in a certain way, whether it's a Docker container or a Python environment, but I can also reproduce it along with the data and the hyperparameters and the code. So that's one way to ensure and track your model environment. There's best practices for model monitoring and model deployment. That's fairly broad. I don't think we can address that here. But then there's best practices for designing your ML architectures. That's probably a whole book in itself. So if there's a specific part that you would like me to address, I can, but not really sure to address that open-ended question.
Thank you. Maybe we'll move on to some other questions. Hima, I saw you had your hand up. Do you still have a question? I'll just press the allow to talk, and if not, we'll move on to the next one.
Yeah, I have a question. So earlier in the presentation, you mentioned that data scientists create ML models and data engineers deploy that model. In the pipeline slide, you mentioned about automatic ML models. So is there something like a model that gets generated automatically, or there is always a human being that creates a model?
So just one thing I do want to clarify is that the data engineer is responsible for essentially moving the data between these stages. The DevOps or the ML engineer is usually responsible for deploying it. I don't know if I was clear in that, but essentially the infrastructure or pipeline that's set up, the data engineer is responsible for making sure it happens smoothly. But the actual deployment part is done by an ML engineer or a DevOps engineer. If a data engineer is usually doing that, that probably means there's something wrong with that team. But to answer your second question, so the model that's generated by the data scientist, so you can have the data scientist that does all the work and kind of does the quantization, puts in the right format and deploying it. So there are tools that allow you to do that. There's nothing that says that can automatically do that. There are tools that would help you to automate as much of that process as possible. The idea with these teams is to have specialized skill sets and folks with those specialized skill sets just focusing on that one aspect. So obviously, if a data scientist has all these skills, they can do that. But the skills associated with DevOps work, for example, are a little different from modeling, which is why we have these separation responsibilities. But there are no tools that automatically says I can just click it and deploy to production. You can do that, but there are steps that you need to take to make sure, one, it's in the right format, it's performing as you expect, and it has all those constraints like latency and memory requirements and everything that's set up. So it's a non-trivial thing. That's usually why you have a full-time staff member dedicated to doing that. Does that answer your question, or is that not what you asked?
Yes. If you could go back to the previous slide, maybe I can just show. Yeah, in here, what's automated model building?
Yes, the automated model building. So what that means is, so you have all the EDA that's, the Databricks AutoML tool is a good example. It performs all the EDA, it performs all the pre-processing of the data. It builds that model for, it goes through a class of models using that AutoML framework. It identifies some of the best performing models. It builds that subject to certain constraints you put into that selection process. You can say, I want the one with the best performing metric, if it's an F1 score or R squared or whatever metric you're using. Or you can say, I don't necessarily want the best performing model, but it is a combination of that performance and solution time. So there's various ways to determine what's sufficient in terms of picking a best model. And then once you have that, it gets put into a certain pipeline. So it goes into a certain component. And for example, it could go into Circle CI or something. And that would actually pick up that model. It will put it into that particular component. And then, now that if you don't have the third stage, it's basically saying it's ready for someone like a DevOps engineer to pick up and put it into that model. If you had automated pipeline building, now that's another level of abstraction where it says a certain number of tests have been passed. It gets automatically packaged, it gets put into this in this format like Onyx, and it gets automatically deployed away. So that's the highest level of sophistication you can get in there. But at the same time, I do want to qualify that by saying, while everything is happening, you still need to be a person monitoring, making sure that things are working properly. So there's another step in there where you have everything ready to be used, but a person needs to actually sign off on it to be reused, to make sure you're not putting something into production, even if that pipeline is pretty seamless. So hence why I say, even when you have CI/CD processes in place, they still as a person in the loop just to say, check this, it looks good to go. And then now that pipeline just pulls everything and then deploys it. So it's a combination of many things, but I still would say person still needs to be in the loop. Does that answer that question?
Yes, thank you.
Thanks. Rick Chen asks, is there a way to apply the deep learning algorithms to the sensitive industries like financial quantitative tradings? Is there a way to make the deep learning algorithms explainable to meet the compliance requirements?
So there are various ways now that allows, for example, sensitivity analysis allows you to determine why you're getting certain results, but it's still not quite as explainable. For example, Bayesian neural network gives you a confidence interval. So it's still not explainable, but it gives you a level of certainty associated with making that decision. Applying that example to healthcare, if you know for a fact that there's a certain level of risk, that risk alone isn't enough. I also need to have a confidence interval associated with that risk. So there are various ways that you can mitigate that, but one, you're talking about techniques, scientific techniques that allow you to do something, and the second one is regulations. So if you say, is there a way to apply it to sensitive industries? Sure, but regulations are made by lawmakers. It needs to catch up to that and say this is acceptable. To my knowledge, I don't think we're there yet. There's still a little bit of hesitation in using deep neural networks for many sensitive industries like the healthcare industry. I might be outdated in my knowledge, but to my knowledge, there's nothing that's currently says you can apply it blindly to many of these industries.
Great. Jife asks, what are the most frequently used machine learning models?
I'm assuming it's a class of models. I'm not architectures again. Is that right? So for example, if you,
yes.
Yeah, so you might be surprised, but most of them that are still, again, my knowledge is from Databricks and our customers, but most of them are machine learning problems as opposed to deep learning problems. And I want to say a large portion of them are solved using scikit-learn. I don't know if this surprises anyone. And logistic regression, linear regression, and the big one, random forest, are the most popular ones. Random forest or tree-based methods are popular for a couple of reasons. One, it's been shown to be highly successful for lots of problems. And I think part of that is because of the relative invariance to scale, and as a result, pre-processing needed for the data. To put it short, there's less work that the practitioner needs to do to get good results using random forest. So I think that's one of the reasons why random forests have been highly successful, as opposed to some techniques like support vector machines, which, if you look at academia, they're classical techniques that are very sound mathematics behind it. One, it doesn't scale as well, and two, it's a little harder to tune those parameters and understand it. So the simpler methods are usually the most widely used, and the most widely used doesn't necessarily need to be the best techniques, if that makes any sense.
Absolutely. Thank you. Maybe time for one last one. Is that all right?
Yep. Sounds good to me.
So Katan asks, what are the average timelines to take the model to production from your experience? Says, I understand this is a very subjective question, but I'm asking just for your experience. So average timeline to take the model to production.
Yeah, that again, it really depends. So I would say the sophistication of teams, if you've not really been in an industrial setting, you might be surprised by. We have customers that are very sophisticated, doing state-of-the-art things, but there's a very small percentage. If I put a number on it, maybe less than 10%. The vast majority of customers are dealing with simpler problems like data governance and how do I scale my problem using Pandas, UDF, and Spark. So the distribution is large. There's no such thing I would say as if I give you that the mean or median value, it would make no sense because the standard deviation of that time at that time scale is pretty broad. You can go, I would say, anywhere from by production, I would assume getting that model ready in the right format, monitoring it, putting into production and a working pipeline. Anywhere from once you have that model built, I would say anywhere from 2 weeks to a year and a half. That 2 weeks is for the team who's already done it before, I would say. And everything is, like I said, we're in this third level of sophistication. It's already done everything, their best practices in place. But generally, I would say there's less than 1% of institutions or companies or organizations that can do that. Most of them are struggling with well, I don't want to say struggle. They're still focused on solving some of the simpler problems like data governance, model tracking, making sure you have reproducible results. We have a long way to go before we can make that process pretty seamless.
That's great. Thank you so much, Srijith, for sharing your thoughts, your experience with us, and for giving us such a great overview of the machine learning pipeline and lifecycle today. So thanks so much. I also want to thank Databricks for hosting the lecture series. Thanks to Tia Foss and to Rob Reed for organizing the series, and to Gary Morphy-Lum for all the Zoom support. And thanks to everybody who joined us tonight. The recording of this presentation is going to be posted on the event page of the iSchool site where you found the link, probably in the next week or two. So again, thanks, Srijith. It's great to hear from you.
I really appreciate you guys giving me an opportunity to give this talk, and thank you for taking the time to listen to me today.
Excellent. Okay, thanks everybody. Have a great night.
Thank you, guys.